So the program of today is that we are finishing the proof of the theorem of Hale-Yoshida. So what's remaining is we have seen two lemmas, and so we have to finish the proof. And then we will go to chapter 3, and we will work on examples, and it will be exercises style. All right, so I recall here the Hale-Yoshida theorem. So again, this is it gives equivalence. So A, the linear operator A, is the infinitesimal generator of a C0 semigroup of contractions. So contractions, again, it's important. So if and only if A is densely defined and closed, and so the resolvent set contains the half positive line, real half positive line, and you have also this estimate for the resolvent, which is defined as lambda I minus A minus 1, the inverse of lambda I minus 1. So the norm on the operator is less than 1 divided by lambda. So we've seen the proof of necessity. Then we started the proof of sufficiency. We've seen this lemma. And so last time we did in detail the other lemma. So now, with those results in mind, are you able to prove that those conditions are sufficient so that the operator A generates a C0 semigroup? And to start, I let you think about that a few minutes. You have this estimate, okay? We have proven that this exponential t a lambda for fixed lambda is a uniform continuous semigroup. So we have this result. And furthermore, we have this estimate. Okay, so with that, can you prove that A generates a C0 semigroup? So I let you a few minutes to think about that. And so I come back later. So we want to prove that A generates a C0 semigroup. So the question is, how from this inequality and maybe some previous work can we propose a candidate S of t who could be the semigroup generated by A? Does somebody have an idea? So so basically what we've seen is that oh, I have something or so what we've seen is as lambda goes to infinity, in some way A lambda converges to A. We proved something like that. So in particular, the right hand side here, what can I say from that? So we proved that a lambda x goes to ax as lambda goes to infinity. This was the first lemma. But be careful, it's only for x in the domain of the operator A, not for all x in capital X. Okay, means what? So capital X is a Banach space. So if I have a lambda x which converges to ax, this is a Cauchy sequence. So meaning that if lambda and mu are large enough, this quantity is as small as I want. So, okay, so for each fixed t, for each fixed x, a lambda, so the left-hand side now, if I add to index with an n, will be a Cauchy sequence. All right, so I have no choice. As lambda goes to infinity, I know that exponential t a lambda x will converge. Okay. So let me just write another thing here. So I'm going to propose some s of t. So, but we need also that we prove that. So we have that. And we have also that for all x in d of a, limit as lambda goes to infinity of a lambda x converges. Okay, so this means that for lambda and mu large enough, this is as small as I want here. And this implies that for each x for xt, this is converging. So what is our candidate? So we set s of t equals limit when lambda goes to infinity. I forgot x. Okay. So this will be my candidate. So I hope now to prove that ST is generated by A. Let's try to prove that. This makes sense because A lambda converges to A. So for each x in D of A, and A lambda generates the semigroup exponential TA lambda. So we hope that when I go to the limit, A will generate the limit of exponential TA lambda. All right, that makes sense. So next, the question is, so now I have defined S of t. It's defined on D of A. It's an operator. Is it a semigroup? Is it linear? Well, yes. So by continuity, so I'm not going to do all the details, but by continuity, you will have that S the T is a semigroup. It will satisfy the properties of the semigroup, and it will be linear. So the next question that's not so immediate is that the construction is only valid for x belonging to D of A. Now, we want to define S of t on the whole x, knowing that D of A is dense in x. So since S of t is a linear operator, a continuous linear operator, we have that the norm of S of t x minus y is less than the norm of S of t norm x y. And also we know by construction that this will be less than 1. So for fixed t, S of t is uniformly continuous. So I can, by this theorem in topology, you can extend it to the whole X because D of A is dense on X. So again, as the t by taking the limit with respect to lambda is for each t is a bounded linear operator, and in fact we have norm of S of t which is less for x in D of A is less than norm of x in dA, and it satisfies the properties of semigroups. So we have the uniform continuity in X for each t. So as the t is for each fixed t, as the t is uniformly continuous on D of A. So by continuity, I can extend it to the whole X. So now we have now S of t is a semigroup on X, not only on dA, but X. And also you have that ST of X is less than X. So now the question that you mentioned is S of t C0 semigroup. So to address this question, okay, this is okay, don't worry. So now is this a C0 semigroup? So we need to prove that ST for all X in X, I'm going to look at this quantity. We need to prove that. So we need so we need to prove that this quantity converges to 0 as t goes to 0. So let's choose a small epsilon here. So there's two things. So what we have an estimate. We know that exponential ta mu x converges to x when t goes to 0. We have more. In fact, we have that exponential a mu t minus identity in the operator norm goes to 0 as t goes to 0 plus. Okay, so I need to do that. So to be exactly rigorous, we are going to do that. So we have that st of x minus x we need also, because we defined s of t as the limit for x in d of a as exponential t a mu. So we are going to do that. Minus s of t x epsilon, where epsilon is in dA and is small enough, is close enough to x, plus st x epsilon minus exponential t a, let's get a mu, x epsilon plus exponential t a mu x epsilon minus x epsilon plus x epsilon minus x. So I choose x epsilon close to x. So I choose that to be less than epsilon. So I don't have a problem with that because exponential t a mu is converging to identity in the operator norm. So for mu large enough, I don't have a problem with that. Exponential t a mu x epsilon is converging to s of t x epsilon for t large enough. And finally, also, this is less than x minus x epsilon. So let's do some transformation here. Is less than, so let me bound that. So I will join this one and this one. Okay, sorry. What do we have more? Okay, let's write it like that. Plus this, actually, I can write it. Yeah. All right, so okay, so two things. So let's say this is smaller than epsilon. I choose my x epsilon to be close to x at a distance of epsilon. So S of t, I didn't choose that, but S of t, in fact, this convergence, you can check that the convergence is uniform with respect to t also. I didn't use that so far, but here I need that. So meaning that for mu small enough, I can put that also less than epsilon for all t in some interval 0t. And since x epsilon, I know also that this is bounded. The norm of x epsilon is bounded because I know so for each t in 0t, so exception doesn't depend on t, so this is bounded. I have no problem with that. And this also, I can put it less than epsilon. So, okay, I can choose that for t, here is the the important point is this t that is converging to 0. That's the point. So let's say we can choose that. So at the end of the day, I can make all this thing less than epsilon, for example. So I can put that, I can ensure that this is, so how many terms? 1, 2, 3, 4. So 4 epsilon. I can ensure that this epsilon 4 and this epsilon 4. So at the end of the day, this is less than epsilon for t close enough to 0. Okay. And here, so there exists t0 super 0. Okay, so we proved that S of t is a C0 semigroup. Yeah, or maybe I said mu small enough. No, it's mu large enough because we have the convergence here. We can make that as small as, sorry, it's there. It's there. We can make that as small as we want if we choose a mu large enough. Thank you for the remark. So just next, so we want to prove that actually A is the generator of S of t. So to do that, so we assume that X belongs to G of A. We'll see later why. And we will look at S of SH of X minus X. And later we will divide by H and let H goes to 0. Let's let H go to 0. So if we do that, by definition, I know that here it's the limit as lambda goes to infinity of that quantity. And then so I can say that this is the integral of the derivative of that between 0 and h. You can check that. And then I just compute the derivative of this. So exponential a lambda s, I remind you that it's a uniformly continuous semigroup. And so I obtain that. And then this is formally, because we have to prove that rigorously, but I expect that as lambda goes to infinity, this line will give this, okay? We will prove that. So once we have that, we divide by h, we let h goes to 0. This is exactly b of x. If b is the infinitesimal generator of s of t, and here I will get exactly ax. If I divide it by h and take the limit when h goes to 0, since s of 0 is identity, I will get ax. So what I get finally is that if x is in dA, then x is in dB, and bx equals dA. All right, so what we are going to do next is to prove that this is correct. So let's evaluate the norm of S T A x minus exponential T A lambda x. And so we want to prove that the convergence uniformly with respect to t in the bounded interval 0 t as lambda goes to infinity. So so we need to write, for example, exponential t a x minus exponential t a lambda a x plus exponential t a lambda a x minus exponential t a lambda x. So this will be less than. So this one I keep. I know that exponential t a x minus exponential t a lambda a x will converge to 0. You know, I need here that x belong to dA plus, and here I got that. So everything is good. Okay, so this converges to 0 uniformly in t as lambda goes to plus infinity. So this goes to 0 with lambda. Okay, so we're almost done. We proved that S the thief is a C0 semigroup generated by B, with the operator B being the same as A for X in D of A. So it remains to prove that, in fact, dA equals dB. So finally, it remains to show that dA equals dB. All right, so to do that, if we go back to the necessity condition. Since B is the generator of S of t, we know that 1 belongs to the resolvent set. Okay, this is one of the point of the theorem. Okay, so since B is the generator of S, we know that 1 belongs to the resolvent set. So lambda I with lambda equals 1, identity my B is invertible and I minus B minus 1 X equals D of B. Next, I minus B for X in D of A, I minus B equals I minus A, because B equals A on D of A. So I get this is equal to that. Oh. So no, it's not B, it's A, sorry. And we know that, so this is just computation. So we know that I minus A okay, so that gives that you, this gives you that I minus b dA equals x, or I minus b minus n of x equals d of a. But with that, it's done. So okay, those are computations. You can check that carefully at home. Okay, so that's it for the we finished the proof.